What's up, guys, and welcome to this video. The video is on equations of motion, specifically with constant or uniform acceleration. Okay, so uniform acceleration just means that the acceleration is constant over a given period of time. Okay, so the way that we tackle these questions is by using what I like to call UVATS. So we have UVATS. So as a combination, they become UVATS when reading it downwards. Okay, so what do all these things stand for? Okay, so our U is our initial velocity. Okay, so our initial velocity in meters per second. Our V is our final velocity. Okay, and that is also in meters per second. Our A is our acceleration. Okay, and the units for acceleration are meters per second squared. T stands for time, that is in seconds. And lastly, our S is displacement. Okay, and our displacement is in meters. Okay, the S obviously means for seconds. Okay, so using all these things, okay, all of these are vectors, important to note, so let's put that in there. So all of these are vectors, okay, and what does that mean? So with vectors, sign matters. Okay, so basically what that means is a positive value and a negative value mean different things. They're not the same thing, okay? So let's get down our equations of motion, okay? So these are our governing equations. Okay, and these equations can only be used for constant acceleration. Okay, so the method of UVATS is only for constant acceleration. So if the acceleration is changing, you cannot use these equations. But if it's not, then we have four equations that we can use. So our first equation is V equals U plus AT. Our second equation is V squared, so the final velocity squared equals the initial velocity squared, plus 2as. Our third equation is going to be S is equal to, so our displacement is equal to our initial plus our final velocity divided by 2 times the time. And lastly, the final equation is the equation S equals U. Oops, there we go, and that just crashed. Okay, so the final equation is S equals ut, so initial velocity times the time, plus a half times the acceleration times time squared. Okay, so these are the four equations. They are on the formula sheet, but you will probably become very familiar with them, especially 1, 2, and 4. Yeah, so if you want to write those down, it'll probably come in handy. Okay, so like I said before, direction is very important. So the first step when we're writing down our equations of motion is to identify which direction, or identify the positive direction. So which direction we're choosing as positive and which direction we're choosing as negative. And we can use different UVATs for different periods of time. But yeah, so with these equations, we should be able to start answering some questions. Okay, so let's see. Okay, so let's do examples in blue. Okay, so the first example, okay, this is probably going to be a very basic example. So let's see, example 1. Let's say a car is traveling at 5 meters per second north when it passes a robot. Okay, at the robot, the car starts to accelerate. At let's say 2 meters per second squared for 5 seconds. Okay, so part A question, let's say A, part A says determine the final velocity. Okay, so let's see what information we're actually given. Let's do it in red. Okay, so we're looking for V basically. So UVATS, because we have constant acceleration, we should probably put that in there, that it has a uniform acceleration. At 2 meters per second. Okay, so our initial velocity was given, and we're going to say that north is positive. So I've put that there. Let's say north positive. Okay, so we've noted what direction we're choosing as positive. So this is 5 meters per second north. So we're going to take that as our positive. So that's 5. Our final velocity is what we're looking for. Our acceleration, at 2 meters per second north for 5 seconds. So let's take the acceleration as 2. The time, here we go, 5 seconds. And our displacement is also unknown. So basically now we just need to find an equation that works for us. So we want V, so let's try V equals U, let's see, equation number 1, V equals U plus AT. So U was 5 plus our acceleration of 2 times our time of 5. So that gives us our final velocity is 5 plus 10, which is 15 meters per second. And it comes out positive, so we know that it is in the north direction. Okay, then the next part of the question says, so part B is determine the displacement. Okay, so what equation can we use for the displacement? Okay, so with these questions, we're going to have the same UVAT here, so I'm just going to have those ones right there. So I want S now. I've calculated V as 15, but I'm going to use an equation that doesn't use V, just in case. So for example, I'm calculating S, so I could use equation number 3. I could use any of these equations, 2, 3, or 4, because they all contain S, but I'm going to pick equation 4 because it doesn't have V, which is a calculated value. Because if I made a mistake in the first part of the question, I don't want that to affect the rest of my question. So I'm going to use the equation S equals UT plus a half AT squared. So U was 5, time was 5 seconds, plus a half times the acceleration of 2 times 5 squared. So S is equal to 5 times 5 plus a half times 2 times 5 squared. And that comes out as 50 meters. And it came out positive, so the direction is north. Okay, if we got question A correct, then using either equation 2 or 3 should give me the right answer. So let's just try equation 3. S equals U plus V over 2 T. So V plus U is 15 plus 15 is our V, our U was 5 over 2 times our time of 5. So what's that? We have 20 over 2, which is 10, times 5, which is the same as 50 meters. Okay, again, north. Okay, so we got the same answers there. So that's just indicating that you can use any of the equations, but sometimes you need to try pick which equation would be best for the situation and the information that you've been given. Okay, so next, part C says sketch the displacement time graph and the velocity time graph. Okay, so let's start off with the displacement time graph. Okay, so we have a ST graph and then we have a velocity time graph. Okay, so actually it might be easier to start off with the velocity time graph because we know the initial velocity was 5, so we can put that in there. Then we know that the final velocity was 15 So that would be up here, 15. And we know that at time equals 0, t equals 0, the velocity is that. And at time equals 5 seconds, yeah, at time equals 5 seconds, our displacement is there. Okay, so now the question is, how do we link up these 2 points? And we know that the gradient is equal to our acceleration, which is constant. So we're going to have a constant gradient. So basically, that's the graph we have. A straight line graph. Okay, that's a straight line. Use some imagination there to see that as straight. Okay, then we have our displacement time. Okay, so displacement time, we know that at time equals 0, our position is equal to 0. So we're setting ourselves at the reference frame of the robot. Okay, then at time equals 5 seconds, so at time equals 5 seconds, we know we're at a distance of 50 meters. Okay, so now the question is, how do we get to that point? Is it a straight line? Is it changing? What does it look like? Okay, so remember that our displacement time graph is based on the area under this graph right here, our velocity time graph. Okay, so if we look at this graph, we can see that initially the area is small, okay, compared to the final area. Okay, at the end, the area is much bigger, so we have a steeper gradient. So initially, it's going slowly, and then it gets steeper and steeper and steeper and steeper. So our gradient gets steeper. Okay, so I hope that makes sense for you guys. Okay, let's do one more simple question, something not too difficult, and then we'll get into some more complicated stuff. Okay, so let's say example 2. Okay, so a car is going right at, let's say, 50 meters per second and stops uniformly in 10 seconds. Okay, so the first part of the question says calculate the displacement. Okay, so let's get our UVATS. Okay, so how can we use UVATS? The first question, it says it is uniformly, stops uniformly. That implies constant acceleration. Okay, so we can use UVATS. Okay, so our initial velocity, and we're going to pick right as being positive. Our initial velocity is 50 meters per second right. Our final velocity, it wants to stop, so it needs to go to 0. Our acceleration is an unknown. Our time is 10 seconds. Our displacement is also unknown. Okay, so what equation can we use for displacement? S equals, let's use U plus V over 2 times the time. So U is 50 plus 0 divided by 2 times the time of 10 seconds. So let's see what that comes out as. That's 25 times 10. Okay, 250 meters. And the answer came out positive, so we're going to say it is right. Okay. Then the next part of the question, question B, says determine the acceleration. Okay, so what is acceleration? So we can use the same UVAT. Okay, so I want an equation that doesn't have S. Okay, so we look for an equation that doesn't have S, and it's equation number 1. We can use the equation V equals U plus AT. V is final velocity, which was 0. Initial is 50. Our acceleration is the unknown, and our time is 10 seconds. Okay, so if we plug this into our calculator, we get acceleration is equal to minus 5 meters per second squared. Okay, what does this minus sign tell me? This is indication of direction. Okay, so my positive was right. My positive direction is right. Therefore, my negative direction is left. So the acceleration equals acceleration equals 5 meters per second squared left. Okay, that would be the final answer. Okay, and does that make sense? Yes, because if the acceleration was in the positive direction, then the bus or the car would be getting faster and faster. So the fact that it's in the negative direction tells us that this thing is stopping. Okay, so those are the simple examples. Let's get into something a bit more complicated where the vehicle actually does different things at different times. Okay, so this is going to be example 3. Okay, let's call this multiple motions. Okay, so let's say a bike is traveling right on a road from rest. Okay, so it accelerates uniformly at 2 meters per second squared until it reaches a speed of 30 meters per second. Okay, then the bike travels at a constant velocity for let's say 5 seconds. Okay, let's actually say 10 seconds until it sees a stop street. Then we can say the bike stops uniformly in 5 seconds. Okay, so lots of information. We've got to dissect this. Okay, so easiest thing to do is to draw a picture. Okay, so we have a bike. Okay, oh, I don't know what a bike looks like. I don't know how to draw it. Okay, so we have a cart instead of a bike. Okay, so it's moving right first. So we're going to take right as the positive direction. Okay, so we can break up this this journey into 3 parts, right? Bike is traveling right on a road from rest. Okay, so initial equals 0 here. It accelerates uniformly at 2 meters per second until it reaches a speed of 30 meters. 2 meters per second squared until it reaches a speed of 30 meters per second. Okay, so that I would say all of this information is for 1. The bike then travels at a constant velocity for 10 seconds until it sees a stop street. So this is all for the second part of the journey, and then the bike stops uniformly, and that's the third part of the journey. Okay, so for journey 1, we can have different UVATs, and for journey 2, we can have different UVATs, and for journey 3, we can have different UVATs. Okay, so for journey 1, okay, so basically, here we go. That's a very horrible stop sign, but basically it gets to 1, 2, and 3. So we have 1, 2, 3. Okay, so we can separate, okay, and in the second part of the question, okay, so let's actually write down the UVATs. Okay, so for 1, our initial velocity equals 0. Our final velocity equals 30, and we're taking right as positive. I've indicated that already. VA is unknown, T is, acceleration is known, actually it is 2, T is an unknown, and S is also an unknown. Okay, so the second part, the bike travels at a constant velocity. What does constant velocity tell us? Constant velocity means that the acceleration equals 0. So basically, do we need UVATs? The answer is no. We can just use our speed equals distance over time equation and velocity, or acceleration is equal to velocity over time equations. So we can use those two equations there. the bike stops uniformly in 5 seconds. Uniformly tells us it is constant acceleration, so UVATS again. Our initial this time is going to be whatever velocity it was here, which is the velocity it was here at the final stage. So our initial now is 30. Our initial velocity when the bike is over here is 30 meters per second. Our final velocity is 0 because it needs to stop. Acceleration is unknown. Time is 5 seconds. And displacement is also unknown. Okay, so question 1, or question A, let's say draw the velocity time graph. Okay, so what does the velocity time graph look like? Let's go through this. Okay, so we have velocity and we have time. Okay, so at point 0, velocity is equal to 0. At time equals some unknown, t naught, the velocity is equal to 30. Okay, and it gets there through constant acceleration or uniform acceleration, so we're just going to join that, like that. Okay, then at some time, okay, we know the time here, let's see the constant, let's see, for stage 2, the time equals 10 seconds, okay, and the velocity equals 30 meters per second, okay, but we know that the time is t naught plus 10 seconds, so t naught plus 10 seconds, it is at a constant velocity. Okay, and then t naught plus 15 seconds, okay, it needs to get back to 0 because it takes 5 seconds, okay, so we go back to 0. Okay, I hope you guys are understanding what I'm saying. So I'm saying this time here is t naught, this time here is t naught plus 10, and this time here is t naught plus 15. So basically, this section right here is 10 seconds plus whatever this section is, and this section is another 5 seconds. Okay, so with that being said, let us calculate the time, the total time. Okay, so my total time, if I look here, is just my t naught plus 15 seconds. So basically what I need to figure out is what is my t naught? Question mark. Okay, so let us think about what equation we can use. We can use our simple v equals u plus at. Our v is 30. 30, our initial is 0. 30 equals 0 plus our acceleration, which was 2, times our time. So if we solve for t, time equals 15 seconds. Okay, so that is actually t naught. Okay, so our total time equals t naught plus 15, so that's equal to 15 plus 15, which is 30 seconds. Okay, seconds. So that is our answer for that question. So the next part of the question says, okay, calculate the total displacement. Okay, so how are we going to do this? So we could use UVATS here, use UVATS, get that displacement right here, use this equation to get that, so that's S1, S2, and S3, use UVATS to get all that, or we can use the fact that we've already just drawn the velocity time graph. We know what these values are. This is going to be t naught, which is 15, 15 plus 10 is 25, and 15 plus 15 is 30 seconds. So we know all these values, so we can use the area under the graph, okay, because we know that is our displacement, so we can use that approach, which would be much easier. Okay, so total displacement equals area under our velocity time graph, which is equal to, so our area is equal to, we have a triangle, which is the half of the base, which is 15, times the height, which is 30, okay, plus base, which is 10, okay, it's a rectangle, 10 times 30, plus another triangle, half base times height, half our base is 5, that value right there, and our height is 30. So the total displacement is a half times 15 times 30 plus 10 times 30 plus a half times 5 times 30, which gives us 600 meters direction right. Our area came out positive, so the direction must be right. Okay, then question D says calculate the average velocity, average speed rather. Okay, so what is our average speed? Okay, so speed equals the total distance divided by the total time. Okay, so do we know what these are? We just worked out the total distance, which was 600, and we know the total time was 30 seconds. Okay, so if we divide these two things, our total speed was equal to 20 meters per second. Okay, and that is a scalar, so we don't need to give it a direction. Okay, so there's that answer. Okay, so the next question, I want it in red. Okay, so the next question, question DE, is going to be draw the velocity. Oh no, we've already drawn the velocity time graph. We can draw the position time graph and acceleration time graph. Time graphs. Okay, so what's usually easier is to draw the acceleration time graph first. Let me put down these axes first. Okay, so this is the position ST graph and our acceleration time graph. Acceleration time. Okay, so the first part of the question, the acceleration is actually given as 2. So for the first, we also know that it's divided into 15 seconds, 25 seconds, and 5 seconds. So it's going to be 15, 25, 5. Okay, so for the first part, we know that the acceleration is equal to 2. Okay, so we have a nice straight line right there. Then the next part of the question, we already noted that there is constant velocity, so our acceleration is equal to 0, and so this drops to the 0 point, and we go straight across. Okay, the next part of the question, we don't know what the acceleration is. We can easily calculate it. Let's actually do it. V equals u plus at. V is 0, so 0 minus 30 is equal to 5 times t, so not t, 5 equals acceleration times t, which is 5. So our acceleration is equal to minus 6 meters per second squared, or 6 meters per second squared left, because it's in the opposite direction. Okay, so the next part is going to be at minus 6. So we drop all the way down, and we go across, and we go back up. Okay, so that's what our acceleration time graph looks like. Now we have to discuss the displacement time graph. Okay, so for the first part of this question, we are increasing speed, or increasing our velocity. Let's just note this quickly. Okay, so for the first part, we have 0.5 times 15 times 30, which is 225 meters. The next part is 300, and so the next part must be 75 meters. Okay, so basically what we know is that at 15 seconds we've done 225. So let's say at 15 seconds we've done 225. Okay, so 225. In the next part, in the next part we get to 525, and finally we get to 600. Okay, now once we have the points, we just need to decide how are we joining them. Okay, so we know in the first part that we have acceleration, right? We have acceleration, it's speeding up. Our area starts out small, so the area starts out small, so the gradient is small, and ends up really big, so the gradient needs to be very big. So small gradient to big gradient, so we're going small to big gradient, right? Then we know we have constant velocity, so no acceleration. So we have constant velocity, and then what we have is we have a big gradient. Okay, big gradient, so it goes from steep, so big area means steep, and small area means shallow, right? So that means we need to go from a steep gradient to a shallow gradient. So we're going steep gradient to a shallow gradient. Okay, and we arrive at our finishing point. Okay, so yeah, this is a bit of a long video. Hopefully you guys have understood everything. In the next video, I am going to go over 2 objects and maybe 1 more question. So let's say 2 more questions in the next video. We're just going to do examples of different scenarios. But yeah, so I hope this helped you guys. Thanks for watching, and yeah.